So thus far, we've talked about collision theory and reaction rate, and that in order for a reaction to take place, reactant particles have to collide with enough energy and with the correct orientation in order to bring about a reaction. And so based on this, we would expect that really increasing the concentration of any reactant should increase the chemical reaction in the same way, and that's just based on increasing the frequency of collisions. However, this view of a chemical reaction assumes that all the reactants taking place, all the reactants in the reaction actually play an equal role. And while this might be true if you just have two reactant particles, especially simple reactant particles like an atom and a monatomic ion colliding, then that might be the case. But there are lots of reactions that we're going to look at that have more than two reactant particles, or that have quite complex molecular structures. And the more complicated the reaction, the less and less probable it is that all of those reactant particles are going to be able to simultaneously collide with the correct orientation and with enough energy. So just statistically, the chances of more than two reactant particles, even just three, colliding in such a way like that is not very likely. And so instead, the theory of how reactions take place, even possibly those that only have two reactant particles, but definitely for ones that involve more, is that most reactions or many reactions actually take place in a series of steps, not just one moment where all the reactant particles collide at once. So reactions can actually be broken down and studied, and it can be seen that there are lots of little mini reactions taking place that get you from the beginning reactants to the end products. And these sort of mini reactions, these steps, are known as elementary steps or component reactions, and they add up to the overall stoichiometric chemical equation. And it's going to work the same way as we've seen in the past with things like half equations, where things that are on both sides of the arrows are going to cancel out, and then we'll get the net chemical equation. When you add up, or when you look at these component reactions, they are collectively known as the reaction mechanism, and they illustrate how the reaction takes place. So they're trying to give you a sense of, the actual steps that the reactants take, and what are the in-between things that form on the way to forming the products. It's worth noting that the reaction mechanism is not taken as truth. It can only be figured out experimentally, and even when it is figured out experimentally, it's just a theory, which means it's just a possible explanation. It is a suggestion. The more data we collect, the more confident we can be in that suggestion, but usually there's more than one mechanism that can be proposed that could match the collected rate data. So they're not proven to be 100% true all the time. Usually they're just theoretical, and there are multiple mechanisms that could also be suggested as well. So to try to illustrate some of the things I'm talking about here with reaction mechanisms, we're going to look at a reaction mechanism that you're supposed to know anyways for the IB exam, and hopefully kill two birds with one stone. So the reaction mechanisms, or the topic, comes from the environmental chemistry portion of the course, and it has to do with the ozone layer, both its formation and its destruction. So the ozone layer is actually just a portion of the atmosphere at the very top of what's called the stratosphere, and it's where there's a higher concentration of ozone molecules than there are in other sections of the atmosphere. That's why it's called the ozone layer. What happens is that in the upper atmosphere, oxygen, which there's a lot of in our atmosphere, is broken down by part of the UV spectrum, part of what we call the UVC spectrum, which has quite short wavelength and therefore quite high energy. And that breaks apart the double bond of oxygen molecules, of O2 molecules, and produces what we call monatomic oxygen, so actual single atoms of oxygen. And then as those single those single atoms of oxygen make their way down into the stratosphere, where there's more oxygen present than there is up here in the mesosphere, then those single atoms of oxygen collide with full molecules of diatomic oxygen, and they actually form O3 molecules, which is what ozone is. So this right here is a reaction mechanism. It's an example of how this takes place. Oxygen is split by UVC light, that's part of the UV spectrum, and gets split into two monatomic oxygen atoms. Those oxygen atoms then go on to collide with oxygen molecules and produce molecules of ozone. So the overall stoichiometric equation involves canceling out things that are on both sides of the arrows and combining like terms. So I have one oxygen at the beginning and two oxygens here, and they're on the same side of the arrow. So overall, we've got 3 oxygen molecules that are turning into 2 ozone molecules. So these are the component reactions or the elementary steps, and this is the overall balanced stoichiometric equation. The intermediate that forms in this reaction is the monatomic oxygen. So those O atoms. Intermediates always cancel out of overall chemical equations when we do reaction mechanisms. So they get formed by certain steps, but then after they're formed, they get immediately used. Although the oxygen does exist as these single atoms for a short period of time, they aren't our starting or end material. So they are called intermediates. Now, ozone also naturally gets broken down. That's one of the reasons why we associate ozone as being a positive thing in our atmosphere. While the O2 diatomic oxygen is absorbing a lot of this range of the ultraviolet light, the ozone molecules absorb a different part of the ultraviolet spectrum. It's not as high energy as the type of UV light that the diatomic oxygen absorbs, but it is still part of the ultraviolet spectrum. It is still high energy, and so it can still cause damage to us, like skin cancer. It absorbs lower energy light because it has a weaker bond. It's got about a 1.5 bond as opposed to the double bond of diatomic oxygen, but it's still an important feature of our atmosphere, and that it protects us and other life forms. So the breakdown is essentially the reverse of the formation. When ozone molecules absorb that kind of ultraviolet light, they split into oxygen molecules and monatomic oxygen. And that monatomic oxygen can collide with further ozone molecules to create more diatomic oxygen. And so if we look at this overall equation, we cancel out the monatomic oxygen, we combine the ozones and the diatomic oxygen, and the overall stoichiometric equation is that 2 ozones forms 3 O2s. So when we break down ozone, we're just forming oxygen, but it's actually just the reverse of the original equation. And so in the end, these two different equations, the formation and the destruction of ozone, actually reach a nice equilibrium. And that's what keeps the ozone layer in balance. This is what normally is taking place in the atmosphere. There's a lot of ozone being formed, and there's a lot of ozone being broken down, and that ends up absorbing a lot of ultraviolet light so that it never makes it down to the surface of the Earth. In the second mechanism, once again, the intermediate was the monatomic oxygen. You can see it canceling out of the overall equation. The ozone layer is really just it's actually a very low concentration. It never exceeds 10 parts per million, so it's really quite tiny. That's all it means when we say it's the ozone layer. It's just this area of the atmosphere with a slightly higher concentration of ozone molecules. While we're on the subject of ozone, we'll cover the destruction of ozone and the cause of the hole in the ozone layer, as we refer to it. The main reasons why we have this whole seasonal hole in the ozone layer is that over time, humans have released chemicals that act as catalysts for the breakdown of ozone molecules. One category of these molecules that cause this problem are called chlorofluorocarbons, or CFCs. For a long time, they were used as refrigerants, and they were used as aerosols, in spray cans and things like that. The reason being they are fairly stable and unreactive gases, which makes them useful in those types of devices because they're not dangerous. Really, at ground level, they're not going to cause problems. However, because they're pretty unreactive, if they do leak out of those things, then they end up sticking around in the atmosphere for a long time and rising into the stratosphere. And once they're there, the carbon to chlorine bonds, which are weaker than the carbon to fluorine bonds in those molecules, end up getting broken first by ultraviolet light. Ultraviolet light is breaking down the ozone, it's breaking down the oxygen, and it can also break down these carbon to chlorine bonds. And once the chlorine is free, it's actually released as what's called a free radical, a species with an unpaired electron. So when the bond breaks between the carbon and the chlorine, it's a covalent bond made of 2 shared electrons. but when it splits, one electron goes with the carbon and one electron goes with the chlorine. And so you end up with, it's actually not an ion, it doesn't have a charge, but it does have an unpaired electron. So it's just a regular old chlorine atom, which is quite reactive. And so usually when you draw a chlorine radical, you draw the chemical symbol of chlorine, and then you just draw that a dot for the unpaired electron that it has. So once this chlorine is released, it starts to lead to the catalytic destruction of ozone molecules, and the reaction mechanism is shown as follows. So here's an example of a CFC molecule. Ultraviolet light causes chlorine to break off from carbons, and now it's a free radical. It will collide with ozone molecules and split them apart, creating molecular oxygen. And also, chlorine is now bonded to oxygen as an intermediate. But this chlorine-oxygen intermediate then goes on, reacts with more monatomic oxygen, makes more oxygen, diatomic oxygen, and releases the chlorine again as a free radical. So let's look at that in terms of chemical equations. The creation of the chlorine radical involves the CFC. There are different ones, but this is one example, being split by the ultraviolet light and creating two different free radicals. So this is a chlorine free radical, and actually this is also a free radical here. They each end up with an unpaired electron. But the species we care about is the chlorine radical. So the chlorine radical reacts with ozone, creating diatomic oxygen, and then also this chlorine monoxide, the ClO. The ClO then goes on to react with other monatomic oxygen in the atmosphere, and it re-releases that chlorine radical and more diatomic oxygen. So if we add together the overall chemical equation, we can see that the ClO cancels out, and actually the chlorine cancels out too. And so the net reaction is that we have ozone and monatomic oxygen forming two molecules of diatomic oxygen. So we think about the destruction of ozone and the hole in the ozone layer as this negative thing, but actually the product is not negative, it's just oxygen. The problem, though, is that the concentration of ozone is being lowered. If we're identifying what is an intermediate in this reaction, it's the ClO is the intermediate. It gets formed, but then it also gets used up in the next step. And the catalyst is the chlorine radical. Now, if you want to distinguish between an intermediate and a catalyst, well, an intermediate is something that gets formed. So it can't appear in the first step. It can't be a reactant in the first step. So it gets formed by some elementary step, and then it gets immediately used. Whereas a catalyst gets used as a reactant and then also gets reformed later as a product. And so overall, the concentration of chlorine is not changing. So a catalyst does not get used up by a reaction. It doesn't mean it's not involved in the reaction mechanism. In fact, it really has to be involved in the reaction mechanism to have an effect. But you'll see it sometimes in reaction mechanisms, and you can spot a catalyst as something that gets used initially and also reproduced later. So that's how I know that the chlorine is acting as the catalyst here. Each chlorine atom can catalyze the breakdown of tens of thousands of ozone molecules, which is why these chemicals that were used for a long time had such a major impact on the ozone layer. There is an alternative way to break down ozone, which is that the chlorine monoxide here, the ClO, itself can also, instead of reacting with monatomic oxygen, it can also react with ozone molecules itself. That also ends up releasing oxygen gas and even more chlorine radicals. So there are different mechanisms by which ozone can get broken down, but you are responsible for knowing at least some of them. So if you're going to latch onto any, it's important to know how the CFCs are broken down and also to know how the chlorine radical affects ozone. So I would focus on these here. An additional category of molecule that leads to the destruction of ozone are the nitrogen oxides. We've already looked at nitrogen oxides as being produced in internal combustion engines when fuel is being combusted. And in addition to leading to smog and acid deposition, both NO and NO2 can lead to the destruction of ozone. And so below are a couple of different means by which they can do that. So this is not one full reaction mechanism. The second one shows a reaction mechanism, a two-step process, but the other ones are actually just balanced chemical equations that show how they could break down ozone molecules and lead to diatomic oxygen forming. So overall, when we talk about reaction mechanisms, here are a couple of rules that we're going to look at for writing. We don't actually have to come up with our own reaction mechanisms, but just for when we look at reaction mechanisms, these are some rules to keep in mind. While stoichiometric equations may contain many reactant particles, each elementary step of a reaction mechanism can only consist of one or two particles at a time. It goes back to that idea of collision theory, and that really steps of reactions are only going to involve two particles colliding at once. So the molecularity of any particular step, that's a bold-faced sort of vocab term, talks about how many reactant species are involved in that step. And so a step that consists of one particle breaking apart is known as a unimolecular step, while one that contains two particles is called a bimolecular step. In the first step of a mechanism, only reactants or catalysts can be used. But then in later steps, intermediates can also be involved. So initial steps can produce these other chemicals that don't exist initially, but then those intermediates get used immediately in the next step, and so they cancel out of the overall stoichiometric equation. If a catalyst is involved in the mechanism, it needs to be involved as a reactant first, and then it must be reproduced at some point later so that it cancels out of the overall stoichiometric equation, because it's not a reactant and it's not a product. And so each elementary step in itself must be balanced, and all of the steps themselves must add up to the overall stoichiometric equation. The last thing we'll look at with reaction mechanisms is considering their activation energy. And so for normal reactions, when we can just consider overall reactions, we think of these enthalpy level diagrams or potential energy diagrams that we've looked at before. And so one that is exothermic would involve reactants converting into products and resulting in the release of energy as heat. And that's because the change is negative, so there's a loss of potential energy, and that's the energy that gets released to the surroundings as heat energy. When we draw these, we generally draw sort of a hill, and that hill represents the activation energy. So the distance from where they start to the top of that curve is the activation energy. And the higher that activation energy is, the slower the reaction is thought to go. On the other side, we can draw an endothermic one where the reactants start more stable and at a lower potential energy. And on the right, we draw the products with a higher potential energy. The enthalpy change is still the difference between the reactants and products. In this case, it's a positive change because energy is absorbed from the surroundings. And the activation energy, people get this wrong a lot of the time, activation energy actually starts all the way down here and goes all the way to the top of the hill. That is the activation energy for an endothermic reaction. Okay, on the bottom, we can put time. Sometimes you'll see other things like reaction progress or reaction coordinate, and the y-axis is either enthalpy or potential energy. In reactions with many steps, every single step has its own activation energy, but the overall enthalpy change is the same as for the overall reaction. So if these are the initial reactants and these are the final products, then the enthalpy change overall is that change here. So we're usually not as concerned with the enthalpy change, or definitely for diploma program chemistry, you're not concerned with enthalpy changes of intermediate steps. You are only concerned with enthalpy changes for overall steps. But it's important that we understand that there are multiple activation energies along the way. So this would be the first activation energy here, and the second would be from here to here. So there's two different terms you can see on this multi-step reaction mechanism, on this potential energy diagram. There are intermediates, which are reacting species that are formed by earlier steps and then continue to go on reacting and eventually turn into other intermediates or products. Intermediates have a range of stability and lifetimes. They can last fractions of seconds, but they can also stick around for days. And but they do actually exist, and they are shown on potential energy diagrams as energy troughs, so sort of valleys within these on the way to getting to the products. Transition states are a little bit different. We haven't talked about those yet, but transition states are the things that are sort of theoretically believed to exist as bonds are both breaking and forming. And they are what we think of existing at the energy maxima on these graphs. So at the very top of these activation energy hills are these things that exist where bonds are only partially in existence. So the new bonds are forming and old bonds are breaking, and those are what we call transition states. We'll look at them more specifically later on in like the organic chemistry topic, but a transition state, is pictured here in this reaction as the bond between the OH and the carbon is forming, while the bond between this carbon and chlorine is breaking. And it's considered to be extremely unstable and therefore having extremely high potential energy. So transition states are always at the tops of these potential energy hills on potential energy diagrams. So the last concept for this video has to do with what is called the rate determining step. When you have multiple steps in a reaction mechanism, there's always going to be one that is the slowest step. There's going to be one that has the highest activation energy, and that's going to hold all the rest of the steps up. So an incredibly important idea to come away with is that the slowest step is the rate determining step. It determines the overall rate of reaction, and it is the slowest step because it's got the highest activation energy. So rate determining step is the slowest step because of the highest activation energy. There are some simple analogies that kind of illustrate this, like this is meant to be sand falling through a very weird hourglass. If sand is falling through this bottleneck here, and then it has to go through this skinny bottleneck here, and then it has to go through this third bottleneck, you can see that the skinniest one is really all that matters. The sand is going to get held up by the skinny one, and once the sand passes through the skinny one, this third bottleneck has actually zero effect on the overall rate at which sand pours through the hourglass, because as soon as it passes through this one, it can very quickly go through the last one. So actually only this bottleneck matters. These other ones don't actually really affect the overall rate of reaction. In a similar way, these tiny funnels with skinny necks hold up the overall reaction rate of pouring water through these three funnels. And so it doesn't matter where you place it really. You're gonna get the same overall reaction because the water gets bottlenecked in the skinniest funnel. So those would be like the rate determining steps of a three-step reaction. So on a potential energy diagram, if this represents a two-step reaction where this is an intermediate and up at the tops of these curves are transition states, this is the first activation energy and this is the second activation energy. So I can tell from this graph that the second step must be what we call the RDS, or the rate determining step. It's the rate determining step because it has the highest activation energy. Particles might be able to get over this first hill, but what really matters is do they have enough energy when they collide to get over this hill, because that hill is bigger. And so since the rate determining step determines the overall reaction rate, it must be that catalysts affect the rate determining step. They provide alternate pathways to the rate determining step, which therefore lower the activation energy and allow the reaction rate to go faster. So when you add catalysts provide lower energy pathways. So this is the new activation energy with a catalyst. If you lowered the activation energy of like this step, the first step that has a smaller activation energy to begin with, you'd still have this big activation energy to get over second. So really adding something that lowered this activation energy of a non-RDS step has no effect on the overall reaction rate, because you continue to have this really slow rate determining step that is unchanged. So a bit of a long-winded video, I apologize, but essentially we're covering that reactions take place in multiple steps. The ozone layer offers us some examples that we are supposed to know: ozone creation, destruction, and how those are in equilibrium, and also the ozone hole being created by CFCs and nitrogen oxides. But that reaction mechanisms illustrate how reactions take place, and that within those reaction mechanisms, each step has its own activation energy, and The activation energy that is highest results in what's called the rate determining step, which is the slowest step of a reaction.